Today we are going to start with law of chemical equilibrium and equilibrium constant. Consider the following reaction. It is a reversible reaction in which A moles of reactant A react with B moles of reactant B and gives C moles of product C and D moles of product D. Small a, b, c and d are numerical quotients of the substance A, B, C and D respectively. According to the law of mass action, rate of forward reaction can be written as R1 will be equals to K1, it is rate constant for forward reaction, and concentration of A and multiplied by concentration of B. Here small a and b denotes the number of moles of reactant A and reactant B respectively. Rate of backward reaction may be given by R2, which will be equal to K2 concentration of C multiplied by concentration of D. Here small c and d denotes the number of moles of product C and D. Since at equilibrium both the reactions, forward reaction and backward reaction rates will be equal, so it follows that the right hand side of both of equation will also be equal, and we can write that K1 by K2, it is the ratio of forward and backward rate constants, will be equal to Kc, which is new rate constant and it is known as equilibrium constant, will be equal to the ratio of concentration of product and concentration of reactant. The next one is thermodynamic derivation of the law of chemical equilibrium, which is the main heading of our lecture today. Consider the following reaction. Again, the chemical potential of a substance in a mixture is related to its activity by the following expression: mu is equals to mu 0 plus RT ln A. It is equation number 1, in which mu 0 is the chemical potential of pure substance in standard state of unit activity, R is the gas constant and T is the absolute temperature. For a mole of substance A, we can write using equation 1 A mu A, which denotes the chemical potential of reactant A, is equals to small a multiplied by the rest of the equation mu 0 plus RT ln A. And similarly, the change in free energy for the reaction, and similarly the same equation can be written for reactant B, product C and product D. In similar manner, the change in free energy for the reaction is given by del G, which will be equal to G product minus G reactant. It means the Gibbs free energy of the product minus free energy of the reactant. On substitution, we get the total of chemical potential of products minus total of chemical potential of reactants, and finally we get del G will be equal to del 0 plus RT ln, and these are the quotient of reactants, quotient of products and reactant respectively, where is the difference in free energy of the reaction when all reactant and products are in their standard state. It is given by del G0 C mu C0, it is the chemical potential in standard state. D mu 0D, it is also the chemical potential of product D in standard state, and mu A0 shows the chemical potential of reactant A in standard state, and B mu 0 is the chemical potential for reactant B in standard state. In equation 2, the factor J is given by this quantity in which the activities of product divided by the activities of reactant stands for the reaction quotients for activities of the product and reactants. A denotes the activity. Del G is equals to del G0 plus RT ln J. It is equation number 3. This equation is called want of reaction isotherm. For the reaction at equilibrium, del G will be equals to 0, and therefore equation 3 becomes as del G0 is equals to minus RT ln J. As del G0 is the free energy of the reaction in the standard state and is constant at given temperature. Also, the gas constant R and T are constant. Therefore, the factor J, which is equal to the activities of product and activities of reactant, is also constant. From equation 3, we have del G0 is equals to minus RT ln K. This equation is also called want of isotherm. The sign of del G0 indicates whether the forward or reverse reaction is spontaneous. Three possibilities depending on the sign of del G0 for the reaction are: if del G0 is negative, then log K must be positive and the reaction proceeds spontaneously in the forward reaction. If del G0 is positive, log K must be negative and K is less than 1, the reverse reaction is then spontaneous. If del G0 is equals to 0, log K will be equals to 0 and K will be equals to 1. The reaction is at equilibrium. Now, it is clear that the sign of del G0 will be different for forward reaction, for backward reaction, and in equilibrium. Thank you.